Welcome back to week 11 of the ma161 calculus. My name is Götz Pfeiffer and this video is about an optimization problem that involves a parabola and two more examples. So in this problem we are asked to find the point on the parabola y squared equals 2x that is closest to the point 1, 4. Again, we start with a diagram. Well, this is a sketch of a parabola which I drew following the graph sketching guidelines that we developed last week. Now on the parabola there's only one critical point, the extreme point here, and so I calculated a few values, a few points on the parabola which I then joined up. So the blue line here is the parabola y squared equals 2x, and on that line I've marked a particular point with coordinates x, y, and there's the point 1, 4, and the question is find on the parabola the point that is closest to 1, 4. So distance between 2 points in the plane is the square root of the sum of the squares of the differences between the x and the y coordinates of the 2 points. Here one point is the general point xy, the other is 1, 4, so the distance is the square root of x minus 1 squared plus y minus 4 squared. That's the function I guess we want to minimize. To eliminate a variable, we note that the point xy in question here lies on the parabola and therefore satisfies the equation of the parabola, and we can use that to express x as half of y squared and eliminate x from the formula that expresses d. Then d is a function of y, single variable, and we'll try and minimize that. Actually, to save us some trouble, we minimize the square of d rather than d itself. Then we get rid of this square root, and if you think about it, finding the place where the square takes its minimum should give us the point where d itself takes its minimum. So here the domain of y is all of R. As usual, we differentiate. So here we use the chain rule again to find the derivative of this function f of the variable y. Differentiate these two summands, and this simplifies to y cubed minus 8. Setting this to 0 reveals 2, and I call it y0 as the only critical point. And the first derivative test for absolute extreme values that we saw in the earlier video then tells us that this value f of 2 equal to 5 is actually the absolute minimum value. So the y is 2 here. The corresponding x coordinate we find by using the equation that we used to eliminate x. X is half of y squared, so half of 2 squared is 2, and so we've solved the problem. The point 2, 2 is the point closest to 1, 4, with distance, with corresponding distance being the square root of the f value at 2, the square root of 5. In the next problem. We watch a man cross a river. A man launches his boat from a point A on a bank of a straight river 3 kilometers wide and wants to reach a point B 8 kilometers downstream on the opposite bank as quickly as possible. Here's two modes of travel. He could row his boat directly across the river to a point C and then run down to B, or he could row directly to B, or he could row to some point between B and C and then run to B. If he can row 6 kilometers per hour and run 8 kilometers per hour, where should he land to reach B as soon as possible? Again, we start with a sketch. There's your river in blue, flowing to the right. Now, for the solution, since there's no information given, we'll ignore the flow of the river completely. We enter into the diagram the information we have. 3 kilometers wide is the river. So the man is here at point A. Across is the point C, 3 kilometers away. And then 8 kilometers downstream is the point B he wants to reach. He can row to any point D between C and B, and since this is a right-angled triangle, we can calculate the distance from A to D with Pythagoras as the square root of this length and that length. That length is 3 kilometers. And we call the distance between C and D x. That's the distance which varies. And that leaves him 8 kilometers minus x to run along the other bank here. That's the setup with the information labeled in the diagram and a choice of a notation being made. We could have labeled the distance between D and B something and regard this as the variable. This is the choice I made. This is my variable. X is the distance between C and D. Then that leaves him 8 minus x to run, and the rowing distance by Pythagoras is x squared plus 3 squared, or the square root of that. Now, we know that speed is distance divided by time. You can use this formula to express the time as distance divided by speed. And in the two modes, we know that, so he's running a distance of 8 minus x at a speed 8. That gives a running time of 8 minus x over 8. And similarly, the rowing time, distance x squared plus 9 square root of, at the speed of 6 kilometers per hour is the square root divided by 6. So what we want now is to minimize the total time t of x, which is the sum of those two, for x in the closed interval from 0 to 8. X could be any distance. It could be x equal to 0 represents the point C directly across from A. X equal to 8 represents the point B that he wants to reach. As usual, we differentiate to find the critical point. The derivative as this form, t prime of x is x over 6 times that square root minus 1/8. To find the critical point, keeping in mind that x is a positive number, we set this to 0, so we set this quotient equal to 1/8, or bringing things across and simplifying, dividing by 2, we get 4x equal to 3 times the square root of x squared plus 9. If we square both sides here and then bring all the squares together, this simplifies to 7x squared equals 81, and of this we extract the positive square root, x being 9 over root 7. That's the critical point. Now, the closed interval method suggests that we should compare the values taken of the t function at the critical point with the values at the end points, t of 0 and t of 8. T of 0 comes out as 1.5. If you set x equal to 0 in these formulas, then 8 over 8 is 1, and the square root of 9 is 3 over 6, that gives 1/2, and 1/2 plus 1 is 1.5. Similarly, t of 8 makes this part 0, and here we get 73, so the square root of 73 over 6, which is approximately 1.42, and at the critical point itself, t evaluated at 9 over square root of 7, we find it's 1 plus root 7 over 8, approximately 1.33. Comparing the three values, the minimum does in fact occur at the critical point, 9 over root 7, which is approximately 3.4 kilometers downstream. That's the solution to this problem. And finally, a problem involving a semicircle. Find the area of the largest rectangle that can be inscribed in a semicircle of radius r. Again, we start with a diagram. This is supposed to be a semicircle in black of radius r, intersecting the x-axis at plus and minus r and the y-axis at r. In this xy coordinate plane, I pick an arbitrary point xy on the circle, and this point determines an inscribed rectangle which has side lengths y here as the vertical side, and the horizontal as x on the positive side and x on the negative side. That's 2x, so that's a rectangle of area 2xy. Also, I've marked here the angle that the point xy sits at on the circle, on the semicircle. And with that angle I can express x as r times cosine theta and y as r times sine theta. You never know, that might be useful. Dealing with points on a circle, polar coordinates is an alternative way to describe them. So we've chosen to represent this semicircle as the upper half of the circle with the equation x squared plus y squared equals r squared. The rectangle corresponding to point xy has sides of length 2x and y, and so an area, capital A, equal to 2xy. You can use the equation of the circle to eliminate y as the positive square root of r squared minus x squared, and then we want to maximize the function a of x, which is 2x times root r squared minus x squared. Here x runs over the closed interval from 0 to r. So, same procedure as usual. We differentiate the equation that describes r, that describes a, in order to find the critical points. So here we use the product rule and the chain rule to find that the derivative of the a function is 2r squared minus 2x squared over the root of r squared minus x squared. This root is always positive, so setting this equal to 0 is effectively setting r squared equal to 2x squared, and if so this gives extracting positive roots, this gives x is equal to r over root 2. And looking at the extreme cases, x equal to 0 or r, there the area comes out to be 0, so the endpoints of the interval are not in the competition here. So we found that the largest inscribed area, the largest inscribed rectangle, has area A evaluated at r over root 2, which if we substitute r over root 2 in the formula that defines A here, is 2 r over root 2 times the square root of r squared minus the square of r over root 2. An expression that simplifies eventually to just r squared. That's the answer to the question. That's the area of the largest inscribed rectangle. It's a surprisingly simple formula after such a complex calculation, isn't it? The largest inscribed area of a rectangle, in the largest area of a rectangle inscribed into a semicircle of radius r is r squared. So it is in fact possible to set up a simpler argument using the angle theta. Expressing the area in terms of the angle, where we use the fact that x is r times cosine theta and y is r times sine theta, a of theta becomes 2r cosine theta times r sine theta, which is r squared times twice sine theta cosine theta, where we might have used this before. The 2 sine theta cosine theta, that's just the double angle formula. That's simply the sine of twice theta. So the area in terms of the area of the inscribed rectangle in terms of the angle theta is r squared times sine 2 theta. And we all know that the sine, the maximum value of the sine is 1. So if this sine takes value 1, then the area is r squared. Simple as. Now, more concretely, we know that the sine takes its maximum value at pi over 2. So here the argument is 2 theta, so we find that the area described in terms of theta is, the maximum value is r squared when theta is pi over 4, and there's no need for calculus at all in this variant of the solution. Next, we're going to look at different kind of optimization, finding approximations to solutions of equations.